Once we start to really get comfortable with the Laplace transform and how we can use it in circuit analysis, we turn our heads to a different topic, and that's going to be transfer functions. So if we consider an RC circuit here, in the time domain, we can convert that to the S domain, and we're going to assume the initial conditions are equal to 0. We get this circuit here. And we know that Laplace transforms turn differential equations into algebraic equations. And we can simply say that the output voltage is equal to the input voltage, and then we have this resistor divider looking thing here. We can simplify that to say that it's equal to the input voltage in the S domain divided by 1 plus S times RC. But consider that term that's not connected to the input voltage, that 1 divided by 1 plus SRC. What does it really tell us? Well, it could tell us how the output relates to the input if we divide the output voltage simply by the input voltage. And this is what we call a transfer function. And it's given by a capital H, and of course it's a function of S. And it's simply going to be equal to the output voltage divided by the input voltage for the circuit that we gave. Now if we take the transfer function back into the time domain by using the inverse Laplace transform, get this lowercase h in the time domain, and we call that the unit impulse response. And similar to how we had this algebraic term in the S domain, we get a little bit different of a term in the time domain if we want the output. It's going to be equal to the convolution of the input voltage with the unit impulse response. So we haven't introduced convolution before, but in general, we say that the convolution of x with h is equal to the convolution of h with x. And to define this star operator, we have this integral here, so we can represent this convolution as this integral. And we know that in the S domain, the output y is going to be equal to x times capital H. In the time domain, we have this convolution. But what happens if we Laplace transform y of t while substituting this convolution here? And this is where the mathematics starts to get a little bit tedious. So if we simply plug in the Laplace transform, we have that integral 0 from the left to infinity, e to the minus st of dt. And then what are we transforming? Well, we're transforming this convolution, which is equal to this entire integral here. So that's inside the brackets. And we could work with either form of convolution. But the first thing that we want to do is swap these integrals. And we're going to say that they're interchangeable as long as you have the right convergence conditions. And we're going to assume that we do, such that Guido Fubini can help us get through this. So simply we can express that initial Laplace transform integral as this here on the right. And we're going to look at what is inside the brackets first. So to do that, we're going to do a simple u substitution and say that u is equal to t minus z and du is equal to dt. Then that integral inside the brackets simply transforms as this. And we can break that into two integrals. We can have an integral from minus z to 0 from the left, and then 0 from the left to infinity. And we know that that integral is just going to be the Laplace transform of h. So we get an integral from the left plus h of s. And don't forget this exponential e to the minus sc that came from that substitution earlier. So what it turns out is that this integral that we still have left to evaluate is 0 if h is a causal function. But we're going to look at why that's the case and why it's equal to 0. So if we have a causal system, we can also represent x and h simply as x tilde times some unit step function and then h tilde times a unit step function. So our convolution really becomes this, where we had these hidden unit step functions in here. Now, this unit step function will collapse this integral from minus infinity. It'll take that lower bound to 0, so that we have this integral here. And if we apply a Laplace transform, we get a similar expression that we had before, where we are going to rearrange the integral such like we did before. And from this, we are going to make another substitution, say that q is equal to t minus z, dq is equal to dt. And if we look at that integral as t goes to 0, q goes to minus z, as t goes to infinity, q goes to infinity. So making all these substitutions, we arrive at this integral here. And simply recall how integrals react when we have unit step functions. And we're going to consider our function that we're integrating smooth as we have in the past. So if that's the case, we don't disappoint the mathematicians too much, but we can rearrange this integral simply where this unit step function will change this minus z to 0 from the left, such that this entire integral looks like the Laplace transform of h tilde of q, and that's going to be equal to h of s. So that's why in this statement here, if h is causal, this integral goes to 0. We're simply left with h of s. So that being said, getting away from the side note, simply we had our original Laplace transform that we're looking at, where this condition now holds true. We can accept that. And then the Laplace transform just looks like this integral minus infinity to infinity x e to the minus sz dz times h of s, where again, if we have causal systems that we looked at before, there's a hidden unit step function in x, so that integral goes from minus infinity to the right condition, so that it looks like a Laplace transform, or we get x of s. And from this, there's two takeaways. One, if we have a circuit, we can Laplace transform it and get the transfer function, capital H, in the S domain, and we can find the input and output relations that way. We're getting to the age-old question, why do we care? Why is this useful? Well, recall for the RC circuit, we had this transfer function here, and we're going to write that in another form that looks like this. And recall that S is the complex frequency. We want to start to look at what actually happens in this circuit. So if S goes to infinity, the transfer function goes to 0. So for high frequencies, the output is equal to 0 times the input, or the output's always 0. And if S is equal to minus 1 divided by R times C, that transfer function goes to infinity. We know that we'd like to avoid infinities in circuit analysis, so maybe there's some stability issues in the circuit around that frequency. And if S equals 0, or we have no frequency, that transfer function is equal to 1, and the output is equal to the input. Now what does 0 frequency represent? It represents a DC source. So if we had a DC 5 volt source, whatever R and C choose to be, doesn't really matter. Because our output, what's that going to be in the DC case? It's going to be 5 volts because there's no current flowing through the system.